Friends, welcome to the 14th lecture in module 3, where we are going to talk about the consequence analysis. This is a lecture in module 3, and we know that in module 3 we are focusing on risk assessment and reliability applications. Friends, we do agree that in case of reliability estimates, it is important one should know the probability of failure, and therefore, the reliability index can be the converse of this, which can be seen as the safety of the system. While estimating the reliability, one is also indirectly interested if the exceedance limit may be of material strength or load capacity, whatever way we may address this, is reached, what would be the sequence of failure what would be the mode or modes of failure, what would be the causes for such modes of failure, and ultimately what would be the effect or effects of those failure on the overall system. If you look at these effects or consequences in terms of economic perspective and quantify risk in terms of economic perspective, maybe that will complete the problem in total. So, we have already seen there are certain set of studies what we understood in these lecture modules of module 3, FMEA, ETA, FTA, etc., where we understood how to get the sequence of failure, how to identify different modes of failure, and how to diagnose the causes for such failure, may be based on experimental investigations or based on experience and expertise of dialogues, or maybe even doing a what if analysis. We have also focused in fact the risk priority in order purely not only based on the occurrence or modes of failure, but also on the effects caused by those failures. For example, if you look at the risk priority number, which is an interesting quantitative outcome of an FMECA study, risk priority number also tells me the effects of those failure modes on the overall system. Anyway, we have been discussing this in different kinds of risk analysis methods. Adding to this, let us today talk about a consequence analysis, which is an explicit application of risk assessment, which can be very commonly used in any industry in general and in particular to offshore industries. In a consequence analysis, what we exactly do? So, in a consequence analysis, which is more or less a qualitative analysis, a number of various models are used. To estimate the physical effects. Of an accident. The accident can be an oil spill, can be release of an hazardous material, etc. Now, these models are used to predict the damage. So, these models are used to predict the damage caused or arise from the failure modes. So, the damage could be of different order, it can be lethality, it can be injury, it can be material loss, varieties of effects can be. So, consequence analysis deliberately attempts to find out the effect or the consequences of the damage caused by different failure modes, in particular to different perspective where risk assessment is also a part of it. So, accident release of flammable liquids, for example, if you consider, let us say accidental release of flammable liquids can result in severe consequences. I mean, this is for example, I am just quoting only one example. It is not necessary that hazardous release of gases do not cause severe consequences, for example, but specifically in offshore structures let us say oil and gas production platforms. Oil and gas production platforms which are meant for exploration and production, even minor accidents can cause very serious consequences. That is unfortunate. Even a minor accident can result in severe consequences. Let us see why the consequence analysis is very important or primarily important in offshore platforms or offshore structures, because this may actually cause or result in shutdown of operations. It may affect smooth functioning of the plant. So, one has got to very clearly understand that the consequences alone need to be seen in a closer window. So, consequences of various physical effects are to be seen in a closer window. The reason is they can even result in shutdown of the entire operation of the platform. Let us look at one series example. Let us say there is a pressurized chemical, which is being released accidentally. The moment it is released, depending upon the flash point temperature, and the conditions prevailing in the platform, because the adverse effect is oxygen is present in plenty. That is one issue. Wind is blowing, which can set fire easily. So, If the flash point temperature is reached for the specific chemical, it will result in ignition. This will result in what we call immediate ignition. Which will cause what we call as a jet flame as a result. Suppose by any chance, if you are able to delay this ignition, if the ignition is delayed, by any chance, then the flammable vapors can also result in what we call as a blast wave. Which causes also overpressure. So, this will have a larger area of spread. So, the moment you have an hazardous chemical present in the plant, which is inevidently present in the offshore oil and production platforms, if that chemical or the gas is released even accidentally, either it catches fire if the flash point temperature is reached, and that will cause serious consequences. If the ignition is delayed by some process or by some conditions present in the platform, it will cause a blast wave and overpressure, which will also create serious consequences by spreading this over a large area around the platform. In both ways, you can easily understand here, understanding the consequences of the failure modes or accidents are more interesting and more demanding than analyzing the risk based on the probability of occurrence and then the consequences. Okay. So, therefore, consequence analysis, which plays a very vital role in offshore industry risk assessment, because this is very important segment where people have to pay close attention in a micro window to really understand what would be the consequential effects caused by the failure of different modes on the overall functioning of the platform. Now, the consequence calculations can be divided. Part 1 will talk about determination of the source strength parameters, part 2 talks about determination of the consequential effects, and part 3 talks about determination of the damage or damage distances. Or what we call as hazard distances. So, kindly pay attention to these areas as explained in a specific example of a chemical release. We are bothered about two intensities of parameters here. One is what would be the devastating consequence caused when it catches fire or results in overpressure, that is one. The second could be how far and how long it would be spread. So, there are three stages. One is to determine the source strength, whether the released chemical will catch fire or develops overpressure or a blast wave. So, that depends upon the source strength parameter, and of course, the conditions prevailing in the platform, which will also add to the strength or weakness of the source strength parameters. The moment I know this, obviously the second part of the calculation, I must be able to estimate the consequential effects caused by this. Will it cause a fire? If it causes a fire, what would be the damage? If it causes a blast wave or an overpressure, what would be the damage? There are models available to estimate the physical damage caused by such effects on any system, maybe structural system, maybe machineries, equipments, maybe human being, etc. Of course, the third and vital part of the calculation should also indicate what would be the hazard distance. It means how far and how circumferentially this damage would spread. So, therefore, friends, risk assessment alone, which gives me consequence as a multiplier, will not be able to throw a broader window in terms of consequence analysis separately. Therefore, in offshore industry, risk assessment also being estimated by a separate QRA, which is also talking about purely on consequences alone, because they have lot of parameters to be indicated and they have lot of serious effects to be diagnosed as a part of the consequence analysis caused by release of any chemical or a gas, which may be purely accidental, non-intentional. So, let us talk about each parameter separately and elaborate them. What is source string parameter? The source strength parameter depends on the condition at which an accident or explosion takes place. At which the explosion or the accident takes place. It depends on the chemical composition of the release. It depends also on the temperature and pressure at which the chemical or the gas is being released, what we call as operational temperature and pressure. It also of course depends on wind velocity and wind direction. It also depends on stability class, usually given by Pascal stability. Pascal stability will give highlighted figures about whether what is the relative humidity in that area, what is the rainfall, what is the day and night temperature, etc. So, it covers all and tries to give me a stability class based on which the strength parameter of the source can be estimated. Let us say for example, in case of an outflow liquid, outflow of liquid, it may be in a vaporized form from a vessel, okay, liquid or a vapor from a vessel or a tank or a pipe, as the case may be. The volume and rate of outflow is also useful. The volume and rate of outflow is also an important parameter. Which is added to the source strength parameter. Also their phase of flow, in what phase it flows, that is also important. In case of only liquid flow, then one is interested to know what is the possibility of instantaneous flash evaporation possibility. One should be interested to know, depending upon the chemical engineering handbook data available for every kind of liquid or chemical being released, the flash point temperature and the temperature at which the flash or evaporation is possible will be indicated. So, if your operating temperature matches with that, so one can estimate what would be the volume of flash which can happen as an evaporation when the liquid is being released as an outflow. Of course, we all agree and understand that all the liquid getting outflow is not going to be evaporated, some will remain in liquid state. Therefore, one should also be interested to know what are the possible dimensions of the collecting pool of the liquid. In fact, we call this as Bund dimensions or Bund volume. So, let us see what is the Bund quickly. Let us say I have a tank where the chemical is being stored which is hazardous. Okay. Of course, the tank will have a base, the tank will be resting, it will be founded properly, okay. That is the base where there are gusset plates which are provided, the wall thickness of the tank is also shown here. Generally, the tank will also have a calibrator which is indicated on the side to indicate the liquid level, okay. It may be an electronic float, there will be again pressure release valves, there will be again safety valves etc., which will indicate some safety arrangements present in the tank. The height of the tank is usually, let us say the height of the tank above the ground, usually where the crude oil or any chemical in process industries like oil and gas is about, let us say 12 to 15 meters, okay. The diameter is about 6 to 8 meters, the diameter can be about 6 to 8 meters, okay. Tall tanks, very large in diameter. Obviously, you know, whenever there is a liquid possible outflow from this tank because of accident, because of fissure, crack or overpressure etc., obviously part of the liquid exiting out from the tank will get evaporated depending upon the flash point temperature of that liquid stored inside the tank, but remaining will have to stay as a liquid. So, the liquid has got to spread all around the tank, okay. If you look at the plan, obviously if this is the tank, okay, all around essentially there will be a protective system, okay. If I cut a section here, let us say that is what I see the tank here. So, I will also have a wall, okay. I will also have a wall. We call this as Bund. So, I have to estimate the pool volume. Based on that, I must fix up the dimensions of the bund and the height of the bund. So, this is possible only when you do a consequence analysis in detail to estimate how much quantity will be now released as an outflow liquid, out of which how much will get evaporated and how much will remain still as liquid for some time, because that liquid should not be allowed to flow further, it should be contained around the tank. One may ask me a question, why it should be contained around the tank? Because around the tank generally we have a provision of running firefighting devices like sprinklers and wetterizers. So, in case it catches fire, these sprinklers can spray water and the fire can be contained in that specific segment, and so the spread of the fire can be stopped. So, therefore, I need to construct a bund, I need to know the volume of the bund. To know the volume of the bund, I must know what is the input data available, how much liquid will fall on the bund, because that practically depends upon how much volume of liquid you have in the tank, out of which how much percentage can get evaporated because of the flash point, remaining how much pool will be formed. The liquid which is staying here is what we call as the pool. So, we need to know this. So, these are all important data which forms as an source strength parameter in consequence analysis. In addition to that, one should also look at the evaporation rate as a function of volatility of the material, based on which the pool dimensions can be fixed, and then the sprinkler design should be done in such a manner so that the wind velocity and the wind direction should be taken care of while designing the layout of the sprinkler system, so that the fire does not spread in the windward direction, but it is contained within the pool area. Okay. So, let us look at the second issue in consequence calculation, what is called consequential effects. Consequential effects depends on various parameters. It depends upon the dispersion relation of the gas in atmosphere, of course, we all know that dispersion relation is a function of the source strength parameter. It also depends on relative density of the gas. It also of course depends on Pascal stability class. And it also depends on topological data of the surrounding area. Because I am talking about the consequential effects not only to the plant, but also to the public near the plant. So, I am looking only also the societal risk. Societal risk is that risk caused by the accident or the consequence of the accident on the plant. Individual risk is the effect caused by the failure on the plant itself or the personnel working in the plant. So, societal risk is much more important, larger in dimension compared to that of the individual risk who are working in the plant. Therefore, I must also know what is the topological data of the surrounding area, what is the population density, what is the age group of the population, how far the spread of the residential area is there, how far away they are located from the plant. All these data should be all accounted for in the consequential effects, which is the second step or the second part of the calculation of the consequence analysis. Interestingly, intensity of heat radiation which is usually expressed in kilowatt per square meter due to fire or levy is actually a function of distance to the source where the accident has occurred. It also depends on energy of the vapor cloud, which is usually expressed again in Newton per square meter, which is now going to be the function of distance to exploding cloud. So, these values need to be computed in the second part of the consequence analysis. Further friends, it is also important to know the concentration of the gaseous material in atmosphere due to the dispersion of evaporated chemical, which is also an important parameter in estimating the consequences. Of course, the concentration of the gaseous material in atmosphere, because this will tell me what would be the effect caused by this dispersed gas to the society or to the public around the plant. Okay. So, these are all true whether the accident is remaining going to be either explosive or simply a toxic release. So, these are true even if the release is a simple toxic chemical or it is explosive. So, the consequential effects throw a brighter window in understanding many parameters which are otherwise not looked upon in detail when you do risk assessment alone, where consequence only becomes a multiplier in terms of estimating quantified values of risk, because we know risk is a product of probability of occurrence of an event with the consequence of that event if it is occurred. So, varieties of types of models are used in risk analysis, they all depends on what is the type of material being released and what the way the material is being handled. Therefore, properties of materials and handling methods definitely govern the choice of risk analysis. Okay? What are those properties? So, risk assessment method through consequence analysis depends essentially on the choice of the material which is being released or handled, of course, the method by which this is handled. So, various factors could be the phase of the material, whether it is gas, vapor, liquid or sometimes even solid. Then the flammability characteristics, of the material, whether is it an explosive or a simple toxic chemical. The third character should be the storage temperature and pressure, at what temperature it is being stored, then the release type, how it is released, whether it is by controlled outflow or it is catastrophic failure. Okay. If it is a controlled outflow, then one should also bother about the pump capacity. You are trying to pump it out, what is the capacity of the pump. The third could be the damage distance, how far the damage will spread. For every chemical or gas being released, there are different guidelines given by the international regulatory bodies which are called as emergency response planning guidelines. For a concentration of the chemical, for a concentration of chemical in parts per million, what would be the ERPG value which is available in chemical engineering handbook. Based upon the ERPG value, one can compute what is called hazard distance using the equations given by Dow, chemical risk analysis. So, one can also compute the damage distances as a part of the consequential calculations which you have done in the risk assessment. Now, kindly pay attention to a specific event tree analysis for a liquid release which is being plotted on the screen now. Let us consider that there is a leak or a rupture occurred in a vessel. The leak or the rupture of the liquid can result in immediate ignition. If it is yes, then it will result in what we call a pool fire or a jet fire. If it is no, then one should be able to confine it. If you are able to confine it, then one can delay the ignition. If you delay the ignition, it can form either a safe dispersion or it can result in VCE, what we call vapor cloud explosion. If the confinement is not possible, if you are not able to confine when there is no immediate ignition, then you check that is it going to ignite further. If it is going to ignite, it results in what is called as a flash fire or a jet fire. If it is not going to ignite, then you can have a safe dispersion. So, one can easily understand a simple event tree analysis, which is also used as a part of the risk assessment, which includes more or less the consequential effects of a specific damage. The damage is, or the effect is leak or a rupture. So, even for a single event of a damage like a leak or a rupture, one can extend a risk analysis using an event tree and try to find out the consequence of that particular event or occurrence of that event in an elaborate manner, as you see in this picture on the screen now. But of course, these kinds of qualitative risk analysis, where we are talking about consequential analysis, have few limitations. Let us say, what are the limitations of such QRA studies? There are few limitations of QRA studies as the approach is changed, which will give you different results. So, the first one is the scenario selection. The scenario selection depends on the expertise on a specific problem. Because scenario selection can change the view of the QRA in total. The second factor could be, which is also a serious limitation, is changes in environmental conditions. Changes in environmental conditions can cause a serious deviation. It can cause a very serious deviation in interpretation of results. Of QRA. For example, the operating temperature or the ambient temperature during the release of the liquid or the gas can be an important factor, which will tell you what is the serious deviation in the results. The next could be operating temperature can be one character. The other could be the humidity conditions present at the release. Which has been assumed in the QRA study. So, all these factors can result in different result interpretation from the QRA studies, and more importantly the wind direction and velocity, because this can affect the results very seriously. Therefore, whatever model we use for consequence analysis or QRA, each model should simulate, or each model will rather simulate different results for the same release scenario. Therefore, if the choice of the release model is not appropriate to the above parameters, then different models will give different risk assessment statements, though there is some commonness between them. In addition, the main disagreement between this, will be the risk acceptability criteria. As I said, in offshore industry, the risk acceptance is pre-declared for every kind of industry, every kind of process unit of an offshore plant. So, depending upon what is the risk acceptability criteria you are proposing, then you have to estimate the risk based on this. There are many countries, unfortunately, even they do not define an acceptable risk level for an offshore industry. Okay? And interestingly, the acceptability criteria is different for different countries also. Therefore, the database that is used for probability estimates can be subjective, and they can be different as well. So, these parameters will however strongly influence the results that we obtain from the risk assessment studies that we just now followed by different methods. So, in this lecture friends, we have tried to understand the consequence analysis, which is a part of risk assessment, which closely gives you a through window of detailing more understanding towards the consequential effects caused by various failure modes on a given system. It also works out the 3 stages, the 3 parts. The most important part is the societal risk estimates which come out from the consequence analysis, which is very important part of this kind of QRA. However, this kind of QRA studies have limitations, and different methods will give you different results provided what model you have been choosing for estimating the QRAs. Therefore, one need to be very carefully select the choice and release of methods and material, and accordingly use an appropriate model to get a better and acceptable risk assessment, because this also depends upon what is the criteria you want to say the acceptability of risk in a given plant. Thank you very much.